So in this part of the lecture, lecture 10C, we're actually going to prove the pattern that I was trying to get you all to notice. So this is going to be something called Euler's Theorem. Basically, what we're going to do is we're going to adapt Fermat's little theorem in order to understand what's going on in non-prime modulus. So if you have so Fermat's little theorem is basically saying, well, if you have a prime modulus, then a to the p minus 1 is congruent to 1 mod p. So for example, 2 to the 6 is congruent to 1 mod 7, or 5 to the 10 is congruent to 1 mod 11, right? Why did that work? And so on Monday, we carefully stepped through the proof of this. The reason this worked is because the multiples of A are all the numbers in mod P. So for example, the multiples of 2 normally are 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and so on, right? And if you do it in mod 7, what you get is 2, 4, 6, 1, 3, 5, 0, 2, 4, 6, 8. Oh, sorry, not 8. That's 1 again. But so on. And so you notice that this was the bean tossing exercise that we did. So whenever you have whenever A and P are relatively prime, which they are if you're in the prime modulus, then you get all the numbers. You get every single person around the circle. Now, of course, in the bean tossing exercise, it wasn't just true for prime modulus. It was true whenever the greatest common divisor of A and N, your tossing number, and the total number of people around your circle was equal to 1. Then the multiples of A are also all the numbers in mod N. So for example, if A is equal to 3, if you're tossing the beanbag around by thirds, and N is equal to 10, you do still get everyone around. And one way of seeing that is if you take all the multiples, 3, 6, 12, 15, 18, 21, 24, 27, 30, and so on. As you go down to mod 10, you get 3, 6, 9, 2, 5, 8, 1, 4, 7, 0. And so this is still all numbers. So you still do get all the people around the circle, even when the number of people isn't prime, so long as the two numbers, the tossing number and the number of people around the circle, are relatively prime. Okay? So going on from that, sorry, my notes are stuck. I'm going to give you an attempted proof, and you're going to tell me what's wrong with it. So I'm going to make a claim, and this is actually going to be a wrong claim, and we'll see why it's wrong later. So 3 to the 9th is congruent to 1 mod 10, right? So if 10 were a prime number, this would be correct, right? Because then we could use Fermat's little theorem. But so what goes wrong when we try to use the same logic as in Fermat's little theorem? So let's try this proof. Well, 3 is congruent to 3 over 1, is congruent to 6 over 2, is congruent to 9 over 3, and so on, all the way to 27 over 9. Okay, and what does this imply? Well, notice that there are 9 numbers there. So if we rewrite 3 to the 9 as all these things multiplied together, 3 over 1 times 6 over 2 times 9 over 3 times ... times 27 over 9. Well, Len, this is also the same as saying this is 3 to the 9 is congruent to 3 over 1 times 6 over 2 times 9 over 3 times, well, you'd have 12 over 4, but you can convert 12 over 4 to just 2 over 4 because we're in mod 10, right? So that's just 2 over 4 times 5 over 5 times 8 over 6, because it's 18 over 6, times 1 over 7 times 4 over 8 times 7 over 9. Okay, so that's just substituting in each of these numbers in mod 10. And so then, of course, but then notice you have all the different numbers because we already said that all the multiples of 3 are all the multiples, or all the numbers. And so this implies that 3 to the 9 is congruent to 1 by canceling out terms. So what went wrong? So I've already told you that this is wrong. Which of these steps went wrong? Or maybe you think that this proof is right. The proof is right. What steps went wrong? Or if maybe it's not just one step, maybe multiple steps went wrong. When did I do something I'm not allowed to do? Okay, so some people think that I'm not allowed to do what I did in C. What did I do in C? All I did in C is I replaced numbers by their modular equivalents. So you are actually allowed to do everything do what I did in C. So, but one of the things you might notice is that there are certain operations that you can't do in non-prime modular arithmetic. And one of those happens to be division, right? So remember, division only works when you're dividing by something that's relatively prime to your modulus. And so here, and here, I'm dividing, right? So notice, like for example, 6 divided by 2. Am I allowed to divide by 2 in mod 10? Or here, or am I allowed to divide by 5 in mod 10? So these are things that you're not allowed to do. So that's what goes wrong. The problem is that in Fermat's little theorem, in the proof of it, we had to do division. And we were able to do division because we were in a prime modulus. But since we're in a non-prime modulus, we're not able to do division. And so whenever you try to do division by something that's not relatively prime, that's not well defined as a division operation. So what are all these? What are all the problems? Well, notice that if the greatest common divisor of a and n is equal to 1, then the multiples of a are all the numbers in mod and arithmetic. So that's already something that we showed. That's something we've shown for a while. Also, we know that the greatest common divisor is equal to 1, and the reciprocal 1 over a exists and is unique mod and in mod and arithmetic. So we can always divide by 8. So for example, 1 over 3 mod 8 exists, but 1 over 2 mod 8 doesn't. And the issue that would happen is we tried dividing by all non-zero numbers in the previous proof, because you had like 3 over 1 times 6 over 2, and so you needed to be able to divide by 0. Sorry, not by 0, by 2, which was not allowed in mod 10 arithmetic. And so the question, of course, is what numbers can we divide in mod n? I say the answer in the chat here, but you don't really have to, because I already told you which numbers you can divide by mod n. You can divide by anything where the greatest common divisor between that number and n is equal to 1. So anything that's relatively prime. So now what we're going to do is we're going to rewrite our previous claim using just this idea of relative primes and see if that works out. So let's see. So our new claim is, well, we have 3 to some power, and we don't know what power it is yet. So let's call it t for now, and we'll substitute in what t is in a moment. It's congruent to 1 mod 10. So we don't know what it is yet, but let's just start trying to prove things. So notice originally we had 3 is congruent to 3 over 1, is congruent to 6 over 2, is congruent to 9 over 3, is congruent to 12 over 4, is congruent to 15 over 5, is congruent to 18 over 6, is congruent to 21 over 7, is congruent to 24 over 8, is congruent to 27 over 9. But this was wrong, right? We already said that this step was wrong. Why was it wrong? Because you can't divide by 2. Can you divide by 3? Yeah, we can divide by 3 because 3 is relatively prime to 10. What about, can we divide by 4? No, we can't divide by 4 because 4 and 10 have a common factor of 2. We can't divide by 5, obviously. We can't divide by 6. We can't divide by 8. So we're only left with these 4 ways of rewriting it. And so I'm going to now make the claim that instead of just using this t here, I'm going to claim that this number ought to be 4. Okay, and that's the basics of my claim. So our claim is, well, then we know that 3 to the 4 is congruent to 3 over 1 times 9 over 3 times 21 over 7 times 27 over 9. And all of these are legal divisions. So we've restricted ourselves to only the divisions that we're allowed to do now. And if we convert it in mod 10 arithmetic, this is 3 over 1 times 9 over 3 times 1 over 7 times 7 over 9. What do you notice about all the numbers on the top and all the numbers on the bottom? So these and these are the same sets of numbers. And so we can cancel them out. And so 3 to the 4th is congruent to 1 mod 10 by canceling terms. And so here, instead of using n minus 1, which was incorrect, because Fermat's little theorem doesn't hold, we instead used 4, since 4 was the number of relative primes, and then somehow things all magically canceled out. Why do these things magically cancel out? Well, we can also prove that. It turns out that they always will for any number, not just for 3 and 10. So I'm going to give another claim now. So the claim is, if the greatest common divisor of a and n is equal to 1, and the greatest common divisor of b and n is equal to 1, then the greatest common divisor of ab and n is equal to 1. Why don't people guess in chat how you might want to prove this? So how might you prove this? What do we know about greatest common divisors? You guys have done a ton of greatest common divisors now. So actually, I normally do chat in orange. Let me rewrite that in orange. So how would you prove this? What does it mean for the greatest common divisor of 2 numbers to be equal to 1? Back on midterm 1, if I asked you to compute the greatest common divisor, what were the different ways you could do it? Oh, is chat stuck? Is chat stuck? Oh, okay. I am so sorry about that. Chat was stuck, and so you guys were all answering, and I didn't see any of that. So I apologize. Hopefully it's updating now. That was a bug on my part. Okay, let me just go scroll through this quickly to see if, let's see. Oh, someone, okay, yeah. So sorry about that. I missed a ton of chats, so haven't found a pattern, just completed my, okay. Yes, this will all be posted later tonight. The proportions are off. Okay, yes. So yeah, so you have 2 different ways of doing it. There was the Euclidean algorithm and also the prime factorization. And so Euclidean algorithm, that one's hard to use here, but using the prime factorization actually works out very nicely. And so we can actually prove this fairly easily using just the prime factorization. So proof, look at prime factorizations. Look at the prime factorizations of A, B, and N. So clearly, A and N have no primes in common. And B and N also have no primes in common. Okay, so if both of those have no primes in common, well, then when you multiply them together, you don't generate new primes. Those are basic multiplicative building blocks. So AB has no primes in common with N. Which implies that the greatest common divisor of AB and N is equal to 1. And I'm going to make one more claim. So this basically means that when you multiply so on the previous slide, a couple slides ago when we were proving this, what we were doing is yes, here it is. What we were doing is we were multiplying together our number 3 with the other primes, right? Or sorry, with the other relative primes. So the other relative primes here were 1, 3, 7, and 9. And so this here was 3 times 1. This here was 3 times 1. This here is 3 times 3. This here is 3 times 7. And this here is 3 times 9. And so what we're doing there is we're multiplying one of the relative primes with all the other relative primes to generate all these different ways of writing things out. And what we just showed is that whenever you do that, you get some other number that's also a relative prime. Okay, so since we only had 4 relative primes, you have to get one of those 4 other numbers. And the last part of the proof is basically, if you let the GCD of, if A and B are both relatively prime to N, and C is relatively prime to N, then AB, and you know that AB is congruent to AC, then you know that B is congruent to C. So does anyone want to tell me in chat why this is true? If AB is congruent to AC, why is B congruent to C mod N? So relatively prime. Okay, you're on the right track. What's relatively prime? So let me give you a hint. If I'm not working in modular arithmetic, if I'm just working in normal numbers, and I tell you that 5x is equal to 5y, why is can I say that x is equal to y? Yeah, why can I do that? Because 5 is the constant. What am I doing to the constant 5 when I go from 5x is equal to 5y and then go to x is equal to y? What am I doing to both sides of the equation? Yes, I'm dividing it out. Exactly. And so what we're doing is dividing it out. And the question is, can we do that here in modular arithmetic? And the answer to that is yes, precisely because it is a relatively prime. So the proof is really easy. It's just because the GCD of A and N is equal to 1, we can divide by A. Divide by A, and then we're basically done, right? Because you just divide both sides by A, which you can do because it's relatively prime. And so this means that each time we multiply by a different relative prime in mod N, we don't get the same thing. So for example, if our set of relative primes is A1, A2, A3, and A4 are relatively prime to N, relative primes to N, then A1 squared and A1, A2, A1, A3, and A1, A4 are all different numbers. Different numbers mod N. So you know that they're all different numbers. But importantly, they're all different numbers, and there are as many of them as you had relative primes. And this means, of course, that you get all of your relative primes whenever you do this procedure. And that's why when we did that, the top and the bottom of the fraction were all the same sets of numbers, because they're just all the relative primes on both the top and the bottom. Is that all right with everyone? Okay, so let's see how much you all remember. One of the things that I'm trying to emphasize now as we get close to the end of the term is that all the pieces you guys have learned are going to be things you're going to are building blocks for the things that we're going to the things we're doing now. So like, for example, on the final exam, I'm not going to ask you to do the Euclidean algorithm. Instead, I'm going to ask you one of these modular arithmetic questions where you're going to need to know how to do the Euclidean algorithm, and you're going to need to know that you need to use it. So which of the following methods tells you how many numbers smaller than n are relatively prime to n? So this was on your midterm, so all of you should know the answer, and hopefully you guys still remember. So is it the Euclidean algorithm? Is it multiplying together the prime factorization? Is it multiplying together the prime of the powers of the prime factorization plus 1? Is it this weird formula down there, which, okay. So it looks like people do indeed remember. It turns out that this here is phi of n is equal to this thing, and this is Euler's totient function. Function phi of n. Okay, and that tells you how many numbers are relatively prime. And so once we have that, that allows us to write out Euler's theorem in full. So Fermat's Eulers theorem was basically, if for a prime p, then a to the p minus 1 is congruent to 1 mod p. So like a to the 6 is congruent to 1 mod 7. For Euler's theorem, what we've done is we've replaced things. We've replaced, just a moment, why are my notes in the wrong order? No, they appear to be in the right order. Okay, anyway, so what we've done is we've replaced things. So for any number, we now know that a to the phi of n is congruent to 1, where phi of n is Euler's totient function. So for example, phi of 10 is congruent to 10 times 1/2 times 4/5, which is equal to 4. And so from that, you know, a to the 4th is congruent to 1 mod 10. And this is because in 10, you had exactly 4 different relative primes, which we listed out earlier, 1, 3, 7, and 9. And indeed, this is we can now we have all these pieces, we can write out the full proof of Euler's theorem. Which is, before we write the full proof, let's go back and connect this with the tables that we were drawing out a moment ago. So if you can compute Euler's phi, so Euler's totient function for each of these, what you should get is that phi of 8, let me do this in a bright color, let's say red. Phi of 8 is equal to 4. And so you notice that the column with the 4s is also all 1s. Phi of 10 is also equal to 4. So you notice this column is there. Phi of 14 is equal to 6, which is why this column is here. Phi of 15 is actually equal to 8. And so you get this column. So the 4 column is also all 1s. And phi of 18 is equal to 6. And so this column is all 1s. Okay, and that was the pattern we were trying to find. And you notice, of course, this is also the number of rows because Euler's totient function tells you the number of relative primes. So it's also the number of different things that will eventually get you 1. So all the other numbers won't necessarily give you 1 when you take the power of it. Okay, let's prove this. So Euler's theorem, for any number n, it doesn't have to be prime. If the greatest common divisor of a and n is equal to 1, then a to the phi of n is congruent to 1 mod n. And the proof, well, it follows the same sort of idea that we've been doing. Just we have to replace the numbers for the 3 and the 10 or whatever with a and n. So let's let a1 through a sub phi of n, because we have phi of n of them, right? So phi of n is some number, say t, or 5 or 6 or whatever. And we're basically saying that a1 through a phi of n are all the relative primes, all the relative primes. Relative primes. Starting from, let's say, a is equal to a1. Then we can write things out. A1, or just a. So a is congruent to a times a1 over a1. It's congruent to a times a2 over a2. It's congruent to a times a3 over a3. And so on, all the way through a times a sub phi of n over a sub phi of n. And notice that this here is, of course, just a1 squared. Oh, sorry. Well, then we multiply this all together. So then a to the phi of n, so where the power is the phi function, well, you can just multiply all these together. So you have a times a1, a times a2, a times a3, all the way through a times a phi of n, over a1 times a2 times a3, all the way to a phi of n. And notice that these, of course, are all the different relative primes. And so they cancel out, which is what we've shown earlier. And so therefore, a to the phi of n is congruent to 1 mod n. Okay, so hopefully in doing this proof, which has been rather complicated, it's involved multiple pieces and is sort of not obvious, you see sort of the way mathematicians think. So mathematicians figured out Fermat's little theorem. And then, of course, once you figure it out, you're like, well, that only tells us what we can do about primes. What about it can we take? What pieces of that proof can we take and apply them to all these other numbers? And a lot of mathematics is about taking specific theorems. I know that 1 plus 1 is equal to 2, 2 plus 2 is equal to 4, 4 plus 4 is equal to 8. And then getting a general rule. Oh, well, if I add a number to itself, that's the same as multiplying by 2. So trying to find these generalizations of specific rules. But now we have that, we can apply this. And this turns out to be quite helpful in the same way that Fermat's little theorem is helpful. So for example, if I wanted to compute 11 to the 16, and I want to claim that this is congruent to 1, well, how do I solve this? Well, do a prime factorization of 60. That's 2, 15, 3, and 5. So this is equal to 2 squared times 3 times 5. Then phi of 60 would be equal to 60 times 1/2 times 2/3 times 4/5. So then phi of 60, when you multiply that all out, is equal to 16. Also, you need to check that the greatest common divisor of 11 and 60 is equal to 1, because otherwise this doesn't work, right? You need it to be a relative prime. But this is easy because 11 is prime, and so it's relative prime to anything except its multiples. So thus, by Euler's theorem, 11 to the 16 is congruent to 1 mod 60. Let me give another example before I have you all try it out. So let's say I want to compute 2 to the 75 mod 57. So remember last time when we had mod 57, because 57 is not prime, things went wrong when we tried using Fermat's little theorem. But now we have Euler's theorem, which is even more powerful. So 57 is equal to 3 times 19. So phi of 57 is equal to 57 times 2/3 times 18 over 19, which is equal to 36. This now implies that a to the 36 is congruent to 1 mod 57 if the GCD of a and 57 is equal to 1. Well, note that the GCD of 2 and 57 is clearly equal to 1, right? So what you can do is you can just divide out 75 divided by 36. So now that you have that, what you can do is you divide out 75 by 36. That's 2, 72, remainder 3. So this implies that, this piece implies that 2 to the 36 is congruent to 1. And this implies that 2 to the 75 is congruent to 2 to the 36 times 2 plus 3, right? I mean, you're just doing the same thing, dividing with the remainder, which is congruent to 2 to the 36 times 2 cubed, which is congruent to just 2 cubed, because 2 to the 36, this piece is just equal to 1. And so then this is congruent to 8 mod 57. So Euler's theorem can be used even if the mod is not prime. Yes, exactly. That's the whole point of it. So Euler's theorem always works. Euler's theorem works so long as your number a and n are relatively prime. So even if n isn't prime, so long as a and n are relatively prime, you can use Euler's theorem to do these faster powers. Can it be used if it's prime? Yes, it can, because when if p is prime, what is phi of p? Well, if p is prime, then that means its prime factorization is just itself, right? So phi of p is equal to p times 1 minus 1 over p, which is equal to p times p minus 1 over p, which is equal to p minus 1. And so Fermat's little theorem is a special case of Euler's theorem. So Fermat's little theorem only works when you're prime, but Euler's theorem, because the totient function is defined for primes, it gives you Fermat's little theorem whenever you try applying it to a prime. Okay, so now I'm going to have you all try it out. So compute 3 to the 84 mod 55. Okay, so it looks like people are making good progress on this already. So let's try to figure this out together. So 55 is equal to 5 times 11. And so phi of 55 is equal to 55 times 4 over 5 times 10 over 11, which is just equal to 40. Also, you can check that the GCD of 3 and 55 is equal to 1. Well, thus, we know that 3 to the 40 is congruent to 1 mod 55, which implies that 3 to the 84 is congruent to 3 to the 40 times 2 times 3 to the 4, which is congruent to 3 to the 4 mod 55, which is congruent to 81, which is congruent to 26 mod 55, which is B. Okay, so once you have Euler's theorem, you can apply it in the exact same way wherever you would have used Fermat's theorem, assuming that all of the conditions are met. So let's have you all try it out on another one. Compute 6 to the 55 mod 27. Oh, wait, I'm sorry. I was on the wrong slide. Let's have you all zero out again. Okay. Okay, so one thing you have to be slightly careful about. I did not say use Euler's theorem to compute 6 to the 55 mod 27. I just asked you what's 6 to the 55 mod 27. So when you encounter a problem like this in real life, which you probably won't very often, but if you go into cryptography, you will encounter problems like this. The answer isn't, if one method doesn't work, that necessarily means that there isn't an answer. It just means that method doesn't work. And sometimes that'll mean there isn't an answer, but not always. So let's try to figure this out. So many of you correctly noted, probably, that the GCD of 6 and 27 is equal to 3. So you can't use Euler's theorem. Well, let's see what happens if we try to use Euler's theorem. So let me put this as incorrect, and let me put a big box. So hopefully it'll be obvious to note that this is wrong. So if you try to use Euler's theorem, you get phi of 27 is equal to 27 times 2/3, which is equal to 18. So you claim that 6 to the 18 is congruent to 1. So 6 to the 55 would be congruent to 6 to the 18 times 3 plus 1, which is congruent to 6 mod 27. So I assume that someone got B because they did it this way without checking the conditions. So this is wrong. But of course, we have a lot of different ways of computing powers. So we have the ways using Fermat's little theorem, we have using Euler's theorem, but we also always can fall back on just computing it directly because we learned how to do that. So if you tried computing it directly, you'd get 6 is congruent to 6. 6 to the 1 is congruent to 36, which is congruent to 9. Oh, sorry, that's 6 squared. 6 to the 4th will then be congruent to 81, which is congruent to 0. Which means that 6 to the 55 is congruent to 6 to the 4 times 6 to the 51, which is congruent to 0 times 6 to the 51, which is congruent to 0. So the answer here is actually the answer here is actually 0. And you'll notice that I tricked you, right? Because I've been talking all about Euler's theorem, and then all of a sudden I give you a question where Euler's theorem doesn't apply. But remember, sometimes these shortcut theorems don't apply, but you can still do things directly. So if I gave you this problem on an exam, then you would have to recognize that Fermat's little theorem and Euler's theorem both don't work, and you'd have to fall back on the old method of computing things. On the other hand, sometimes I'll ask you to use a particular theorem, in which case you can say this theorem doesn't apply. But other times it just gives you a problem, and you need to figure out that Euler's theorem doesn't work. Can 0 be an answer? Yes, it absolutely can be. So one thing to notice, though, is if Euler's theorem applies, then 0 won't be an answer. But if Euler's theorem doesn't apply, then, well, yes, it can be, as we just saw. So in this particular case, the answer is actually 0. Okay, and on that tricky note, I am going to let you all have a, let's say, 5-minute break, since I have a couple more, let's say 7-minute break. So be back at 10:37, and then we'll finish off by talking about roots using Euler's theorem, like we did with Fermat's little theorem last time. So have a break, and I'll see you in a couple minutes.